Salam, it's Fatima Garba Yusuf again, and this is Electronics. So we're going to solve another example, and it involves comparing engineering stress and strain with through stress and strain. If you can recall in our earlier video, which involves the derivation of the formula for through stress and through strain, we actually showed a graph which shows how a plot of through stress and through strain compares with a plot of engineering stress versus engineering strain, and we saw that the graph of the true stress and true strain was actually steeper, meaning it was above the one of engineering stress and engineering strain. So we want to see this numerically, like which values are higher, which values are lower, and so on and so forth. Now this is an example, and this is a low carbon steel specimen, has the following test values, and from these values you'll actually be able to conclude that it's actually a tensile test, because the original diameter is greater than the final diameter, meaning the length has increased while the area has decreased. So we're asked to compare engineering stress and engineering strain with true stress and true strain values. Now to do that, we're going to first calculate engineering stress, we'll calculate engineering strain, and then it will be sensible in this case to use the formula for engineering for true stress and true strain that involves values of engineering stress and engineering strain. So first we're going to calculate our engineering stress, which is depicted by, let's tag this as solution. So we're going to first calculate the value of engineering stress, which is represented by this symbol sigma, and its value is F divided by original area. In this case, our F is actually applied load, that's 17,000 pound force. Now if you look at these units of these values, we'll see that they are in imperial units, and for us to calculate our stress, this will be in pound force, while this will be in inch square. This double quotation mark represents inch, so our stress will be in pound force per inch square. As for our engineering strain, there is no need for much conversion, because our units will all cancel out. So our value of engineering strain is actually going to be our extension divided by original length, but then our extension is going to be final length minus original length divided by original length. But if you'll notice that in this question we're not given anything related to length. So what did we say we are going to do? We are going to actually either use the formula for true strain to calculate our engineering strain, or we can split this into two. Our LF minus LO over LO can be written as LF over LO minus LO over LO. Now this LO over LO of course will cancel out to give us 1, so we are left with LF over LO minus 1. Now if our engineering strain is LF over LO minus 1, we can simply rewrite this LF over LO to give us AO over AF. And how did we do that? Using our formula that implies that our volume is going to be constant, that's VO is equal to VF. Now if you cross multiply this, it will actually give you AFLF equal to AOLO, which depicts the constants of this volume. So you can see, even though we're not given our length, we can still calculate our engineering strain using this by saying our engineering strain is equal to AO over AF minus 1. Or there's actually another formula that we can use to calculate our engineering strain by first calculating our true strain. And how does that work? That works by first, we know the formula for our true strain is actually ln of, in this case it will be A over AF All right. But then we can note that up here we have an expression that shows us that engineering strain is equal to AO over AF minus 1. So we are going to manipulate that to help us to calculate our engineering strain. That is to say, if you want to bring AO over AF out and make it subject of the formula, it will relate our engineering strain and our 1. So to bring this AO over AF out, we can take the exponential of both sides. This is because when you exponent any natural log, it will cancel out. So this lane will cancel this, and we'll be left with exponential of our through strain is equal to AO over AF. But then from this formula here, our AO over AF can be made subject of this formula. Instead of saying engineering strain, instead of saying engineering strain is equal to AO over AF minus 1, AO over AF can be made subject of the formula by saying AO over AF is equal to, you take this minus 1 over here, equal to engineering strain plus 1. I don't know why I keep interchanging this. Anyway, so this can relate our engineering strain with our engineering strain with our true strain. So in case you decide to first calculate your through strain using this formula, you can then go back and calculate your engineering strain by saying your engineering strain is now equal to exponential of through strain. Then you take this to the other side, it will give you minus 1. Anyway, let's first calculate our engineering stress first. To do that, we'll say our engineering stress is equal to, what is our force? It's 17,000 pound force divided by our area. Our area is going to be the original area, which involves the original diameter 0.5 inch. So our area will be pi times d squared, that's 0.5 squared over 4. Simplifying this gives us 86,580.29 pound force per square inch. We can write this in standard form, but to minimize our errors, we can leave it at this. Let me divide this into 2 so that they don't. So that's it for the engineering stress. For the true stress, when we derived the formula for true stress in our video on the derivation, we calculated our true stress as the formula will just be our force, our applied force won't change, divided by our final area. So we can either divide our applied force to the final area, that we'll need to calculate our final area using the final diameter, or we use the other formula which states that you multiply your engineering stress by your LF over LO. And in this case, since we don't have our L's, it will be our engineering stress multiplied by our AO over AF. So each of these you use will give you the actual value of your true stress. So since in the previous video we used this one, in this one we'll use this one, and you are free to go and cross-check with the previous formula to see if you will get the correct answer. So in this case, our true stress will be equal to our engineering stress, that's 86,580.29, multiplied by our original area over final area. Our original area will be pi times 0.5 squared over 4, while our final area will be pi times 0.472 squared. 0.472 squared will be pi times 0.472 squared, right? Divided by 4. So, as I mentioned in the previous video, you can separate these values of AO, AF in case you are solving for an essay question so that you will not lose out on any marks. Here we are trying to just do it quickly and minimize the use of space. So here when you calculate this, you can use your calculator. It's 6580.29. When you multiply your numerator, it will give you 0.196. 0.196, while your denominator will give you 0.175. 0.175. So when you say 0.196 divided by 0.175, it will give you 1.12. And when you multiply by 1.12 times your 86580, your 86580.29, that's your initial value of your engineering stress. You'll be left with your true stress as 96,969.9, and to be in pound force per inch square. Meanwhile, as these values are prone to error because of the use of pi and the divisions and the decimals, you can minimize your errors by just cancelling out these pi's in your calculation. This pi will cancel this pi, and here, since you have divided by 4 in both numerator and denominator, you can also cancel it. So we'll be left with 0.5 squared divided by 0.472 squared, right? And though that will also give you 1.12, but it's more or less more along the lines of 1.122, and that will change the value of your true stress a little bit by giving you your value as 97,000 and something. But then that's not much of a big deal, because if you were to approximate this, it will give you 97.0 times 10 raised to the power of 3, right? Pound force per inch squared. Likewise here too, if you were to approximate, this will give you 86.6 times 10 raised to the power of 3 pound force per inch squared. So that's it for the engineering stress and the engineering strain. That's it for the engineering stress and the true stress. Now, if you calculate or if you compare the values, you see that your value of engineering stress, as we saw in that graph, is actually less than your value of true stress. And why is that? It's because the ratio of your original area to the final area is actually greater than 1. That's the area actually decreased. Because the length increased, the area decreased. And because that happened, since your original area is the one at the top, then the fraction will give you a number that is greater than 1. And when you multiply any number by a number that is greater than 1, it will increase. So that is why your true stress is greater than your engineering. Your true stress is greater than your engineering stress. All right. Now let's go to the section on strain. So to calculate, you can either use this formula. We have a number of formulas here. We have this for the calculation of engineering strain, but here we need to calculate our true strain first. And then we have the other one where you just calculate your engineering strain by saying your engineering strain is equal to this AO over AF minus 1. So here we're going to use the simplified version that involves our original area and our final area. So what did we say we are going to do? The solution for this, in our solution for our engineering strain, we have it's equal to AO over AF minus 1. So our AO is actually equal to pi times 0.5 squared over 4. But then when we list it out, we see that there are common values in our numerator and the denominator. So this will help us to cancel out and reduce the error. In doing that, we can say our engineering strain is equal to pi times 0.5 squared over 4, right? 4 will come down, then divided by pi times 0.472 squared divided by 4. So this pi will cancel this pi, and this 4 will go up while this 4 will come down. So you see that they can also cancel. So, and then this minus 1, everything over here minus 1. So you are left with actually 0.5 squared divided by 0.472 squared, then minus 1. And when we calculated it, when we were trying to find our true strain, we got 0.5 squared divided by 0.472 squared to be 1.122. Alright, so in this we are going to substitute 1.122 minus 1 to give us our engineering strain. Hence, so we have 1.122, our engineering strain equal to 1.122 minus 1, which is obviously equal to 0.122, and that's unitless. As for our true strain, use ln AO over AF. This will be easier because the other formula is for when you have your true strain already and you're trying to look for your engineering strain. So what we're going to do is we're going to say our true strain is equal to ln of AO over AF, and of course we've already calculated AO over AF countless times, and it gave us 1.122. So this is going to be equal to ln 1.122. all right, so the ln of 1.122 gives us 0.115. all right, it gave us equal to 0.115. Now in this case we can see that our engineering strain is greater than our true strain. So that's it for this video. We calculated the value of our engineering stress and our true stress, as well as our engineering strain and our true strain, and we compared the values, finding out that our engineering stress is greater than, concluding that our true stress from the calculated values is greater than our engineering stress, while on the strain side we have our engineering strain greater than our true strain. So with this, we've come to the end of this video. Feel free to check out the previous videos and also practice by yourself. We will solve one more problem on this and we'll be good to go. Thank you for watching.